Okay, so for today we've got lesson 7.2 with a little star. It's in a grayed out section in our textbook. Here's our learning target. I can differentiate and integrate functions with the natural log. And speaking of the natural log, here's how we begin with a definition. What if it is given to you that the natural log of x, we think of that as an accumulation function, as the integral from 1 to x of 1 over t dt for every x greater than 0. And you can see we've got a graph listed down there. Of course, an accumulation function would be representing some function in general. We're making a bold claim here. We're saying, by definition, that's the natural log function. Now, with that in mind, we can immediately jump back to a previous chapter, not the one that we just completed, but the previous one in chapter 5. We dealt with taking derivatives of accumulation functions. And I hope you remember, when you just have an x and any constant down below, the shortcut is just to substitute that x straight into the integrand. And oh my goodness, that means that the derivative of the natural log of x would be 1 over x. Now we're going to talk about that right here. This is that theorem. Memorize that for sure. You want to know that when you take the derivative of the natural log of x, it's 1 over x. And we can have a little picture of a graph of the natural log of x that would have this type of a shape. That's maybe just to help us see where those values are going to be coming from that accumulation function. You could begin to just trace it out, even with an f and int, point by point by point. Trust me, you'd get this shape. But look at this theorem down below. If u is just some arbitrary function, g, and we just write it a little bit more simply, and g is differentiable, it shouldn't surprise you that when you take the derivative of the natural log of g of x, which we're calling u, we're going to use the chain rule. We'll say that's 1 over u times du dx. And kids probably are thinking, hey, well, that's wonderful, that's good. Here, though, for step 2, is the amazing, more powerful follow-up. We can actually go and say the natural log of the absolute value of u, when I take the derivative of that, I get the very same thing, 1 over u times du dx. Right now, that might seem far-fetched. You might say, hey, if u was a positive value, perhaps I'd believe that. Because when u is positive, if that function is positive, would you agree we're just back to numeral 1 right here? But that then begs the question. That's why I've written off to the side right over here that the absolute value of u could be u or opposite of u, depending on whether the function is positive or negative. Let's just hypothetically say that we were investigating when u was less than 0. If that were the case, then the natural log of the absolute value of u would really be the natural log of negative u. Now, at first glance, kids can get upset when they see that. They'll say you can't have negatives inside of a natural log function. But realize that you could, in fact, get that to come out. That's why we have a graph. I do want to just show you why I even brought the graph up to get you started. Usually kids won't have any issue with the natural log of x. They'll say, hey, you graph that thing, and we get something that looks like so. Maybe a zoom decimal might make it look a little bit nicer. Sometimes kids will say, well, you could never have a negative inside. Well, wait a minute. What if that interior was negative? That means that our actual inputs would have to be negative to be able to evaluate them, right? So it would be possible to get that to be true. So it's possible that you could say, hey, let's take the derivative of the natural log of negative u. Well, according to following Roman numeral 1, Wouldn't that be negative 1 over u times the derivative of negative u? But wouldn't the derivative of a negative just allow us to pull that negative out in front? So this negative here would cancel with this negative. You're right back to here. So that's a very quick proof. In the future, just remember, whether you are taking the natural log of u or the natural log of the absolute value of u, the derivative is always 1 over u times du dx. Well, enough of just the talking about the theory. Let's actually see this in practice. Let's go ahead and say, here's example 1. Let's take the derivative of the natural log of x cubed minus 4x. What do you think we'd get? 1 over x cubed minus 4x. You always go 1 over that argument. Chain rule. Now we're going to take the derivative of the inside. Guys, what's the derivative of this inside? 3x squared minus 4. What's our final answer? Well, plain and simply, 3x squared minus 4 over x cubed minus 4x. We are done. Take a look at example 2. This is the one that maybe makes kids feel a little uncomfortable. They'll say, oh no, that absolute value in there. Guys, it's as if it wasn't there at all. The derivative of number 2, it would be the same derivative as if the absolute value wasn't there at all. So help me out. What do you think f prime would be? We're going to start by going 1 over 4 plus sine x times, hey, what's the derivative of that inside part? Cosine of x. Hey, look at this. We're done. Oh, my word. So, take a look at this. This maybe seems the most out of the ordinary. The laws of natural logarithms. Logs don't go away. I think you're going to be glad they don't go away pretty soon. Look, if I have the natural log of p times q, the multiplication of p times q, we can say, look, we could write that as 2 logarithms. The natural log of p plus the natural log of q. When we're dividing p over q, we can turn that into the natural log of the numerator minus the natural log of the denominator. And we'll have 2 logs. Hey, here's your power. We can drop it like it's hot as we joke around. That's r times the natural log of p, right? Okay. So, look at this. Number 3. Nightmarish looking. Sometimes kids are like, oh, Mr. Dobner, please, please, please don't tell me that we have to go 1 over that function and then multiply by the derivative of the inside. Yeah, you could do that, but let's do it in a more intelligent way. Let's do this in a more intelligent way, using the properties of logs. Oh my goodness. Wait a minute. This would become the natural log. Would you agree this is x squared plus 1 minus the natural log of 9x minus 4 to the second? Oh, this is looking better by the moment. Sometimes kids would almost think, as they're beginning to learn logs, why on earth would you ever want to take 1 logarithm and turn them into multiple logs? Aren't you making the problem more complex? Actually, if you're doing calculus, you're making it way simpler, aren't you? By far, you won't have to use the quotient rule. Oh, my word. Well, wow, this is natural log of x squared plus 1. A square root, would we agree that's a 1/2 power? And tell you what, I'll even drop down this 2 right here. We'll just clean this up. Tell you what, let me even recopy this way. And guys, we're almost ready to very simply take our derivative. Something that would look horrific, something that would just be a monstrosity of a problem, becomes way better. Look, y prime. Kids are probably thinking, well, you got to take 1 over that thing. Yep. Don't forget the chain rule. What's the derivative of the inside? 2x, right? You'll say, well, now I've got to go 1 over this thing, 9x minus 4. Derivative of the inside, what's that? A 9. Hey, let's have the 2's cancel out. This would be x over x squared plus 1. How about we get this 18 all over 9x minus 4 and happily say, we're done. Okay. Well, sometimes kids look at number 4 and they'll say, oh, wow, I don't see a log there. Oh, if only the log was there, then it would be a nice problem like before. Make it so indeed. Make it so indeed. Look, this is what we'll do. We'll say, oh, man, I want a natural log there. Put it there. All of a sudden, kids are looking at this saying, are you kidding me? You mean this problem that we learned with the product rule and the chain rule way back earlier in the year? You mean we could have done it this way? Yes. Oh, wow, knowledge is power. Would you look at that? Wow. Okay, well, let's start breaking this thing up. This becomes natural log of, tell you what, how about I combine a couple steps? You know, we've got the video going too. Want to be our best with time, of course. But would you agree a multiplication inside the log means I can write an addition of 2 logs? Right? And we're going to take those powers, we're going to say, hey, drop them down. Bring down that 1/2 natural log of 4x plus 7 plus 3 natural log of x minus 5. And here's where we have to be careful, guys. We can't, this is called logarithmic differentiation, by the way. It's saying, hey, how about we introduce a logarithm on both sides to make our life easier? Well, there's one little price to pay. Look at this left-hand side. What's the derivative of the natural log of y? Implicit, remember, 1 over y, dy dx. You got to take the derivative of the inside. Oh, is this good? Look at what we're reviewing right now. This is why we're doing late transcendentals. We're reviewing so much. It's only going to help us as we get ready for that big test. So look, we're going to say this is 1 over 4x plus 7. Don't forget the chain rule. Derivative of the inside is a 4. Here I'm going to say 1 over x minus 5. Derivative of the inside, happily, is just a 1. Wow. Well, a 2 cancels with a 4, leaves you with a 2. So tell you what, we're a little bit squished in here, but we'll make it nice. This is a 2 over 4x plus 7. Here's a 3 all over x minus 5. And please understand, ultimately, you're trying to find dy dx. And I don't have that on the left-hand side, sad to say. What do you think we have to do to get dy dx? Multiply both sides by y. Now, we're almost done, guys. We're almost done. You can say, well, my goodness, that's great, but imagine we're finding a tangent line slope. It's one thing to be able to say plug in your x-coordinate and your y-coordinate. Traditionally, our derivatives, if we can, we'd like to have them all in terms of x, with respect to x. And then you'd say, what is y? Oh, it's this ugly thing right here. So let's just rewrite it and say, here's this big mess of radical 4x plus 7 times an x minus 5 to the third. And here are our brackets. And guys, that's your answer. No quotient rule. No tears in taking that derivative, hopefully. So a real ugly problem can be done considerably easier. We doing okay? Yeah. All right, about half a minute left on the video. Just have to tell you that the most general derivative that we're going to have of the natural log involved the absolute value. So if we were working in reverse, we must include the absolute value. What I've highlighted in green here, please make sure you memorize. The integral of 1 over u du is the natural log of u plus c.